Welcome back, video 2 of 3 for Unit 2. Two stories in this video. First, estimation maximum likelihood versus Bayesian thinking, settled with a coin flip experiment, and the 8 challenges that pushed the world from classical machine learning to deep learning. Then we start building the biological neuron, its artificial twin activation functions, and the legendary XOR problem, the 4-row truth table that froze AI research for a decade, and the single idea that thawed it. Let's go. Now, how do we actually estimate parameters from data in a principled way? Method 1: Maximum Likelihood Estimation. MLE. The idea in one sentence: choose the parameters that make the observed data most probable. The bell curve picture: imagine trying different bell curves over your data sample. Poorly fitted curves: the data looks improbable under them, low likelihood. The best fitting curve: the data looks most probable. MLE picks that one by maximizing the likelihood function. Concrete: flip a coin 10 times, see 7 heads. Which probability P makes that outcome most likely? Try 0.5 mediocre, try 0.7 maximal. MLE says P hat equals 0.7. Exactly the intuitive frequency, now with a formal justification. One practical note: the likelihood is a product of many probabilities and products or small numbers under flow, as Unit 1 taught us. That's why everyone maximizes the log likelihood instead. And a secret for later: minimizing cross-entropy loss is maximum likelihood. Every classifier you train is doing MLE. Method 2: Bayesian statistics estimation with beliefs. The Bayesian framework uses prior knowledge and observed data together. Same Bayes rule as Unit 1, but now applied to parameters. The cast, the prior, what we believe before seeing data. Example: this coin is probably fair. The likelihood, how probable the data is under each parameter value, 7 heads and 10 flips. And the posterior, the updated belief, likelihood times prior, normalized. Watch the fair coin prior at work. The data alone shouts 0.7. The prior whispers 0.5. The posterior lands around 0.63 between them. The prior pulled the estimate toward fairness. And the beautiful dynamic: flip 1,000 times and the data overwhelms the prior, the posterior converges to the frequency. Priors matter most when data is scarce, which is precisely when you need help. Key contrast with MLE: Bayesian returns a whole distribution over the parameter, carrying uncertainty, not just one number. The two estimation philosophies: face-to-face, prior knowledge. MLE: none, data only. Bayesian: yes, that's the whole point. Output: MLE: a single best value, a point. Bayesian: a full posterior distribution. Our coin, 7 heads and 10, MLE says exactly 0.7. Bayesian, with a fair prior, says around 0.63. Small datasets: MLE can overfit the sample. Bayesian: the prior stabilizes the estimate. Large datasets: both converge, the data drowns the prior. So which is better? Wrong question. With lots of data, they agree. With scarce data, priors help. And a lovely secret connecting to Unit 3, L2 regularization is mathematically a Gaussian prior on the weights. Bayesian thinking hides inside ordinary training. Before we build our neural network, one final question for Port 1: why did the world move to deep learning at all? 8 challenges broke traditional machine learning. Here are the first 4. 1. High-dimensional, complex data, images, video, speech, text. Classical models, SV miss, logistic regression, decision trees struggle with the dimensionality and the tangled non-linear patterns. Deep networks handle them through hierarchical features. 2. Manual feature engineering. The old pipelines needed hand-crafted features with names like SIFT and HOG. Entire PhDs were spent designing them. Slow? Problem-specific? Expert-dependent. Deep learning extracts features automatically. 3. Limited model capacity. Classical models assume simple decision boundaries. Deep networks, with many layers and non-linear activations, can approximate a and y function. That's the universal approximation theorem. And 4. Scale. Social media, e-commerce, medical imaging generate millions of samples. Traditional models plateau as data grows. Deep models keep improving. That difference in the scaling curve alone explains the industry's pivot. Challenges 5 through 8 and how deep learning broke through. 5. Computation arrived. GPS, TPS, distributed training, cloud computing. Deep models existed on paper for decades, suddenly they became trainable. 6. The curse of dimensionality. In very high dimensions, data becomes sparse and distances lose meaning, classical algorithms break down. Deep networks fight back by learning compact representations, embeddings, pooling. 7. End-to-end and learning. The traditional pipeline had 4 separate hand-tuned stages: pre-process, engineer features, select, model, classify. Deep learning learns everything jointly, raw data to output. Fewer stages, fewer human errors, and 8. The breakthroughs themselves. Imagine it. Speech recognition, machine translation, AlphaGo. Success stories recruited the whole industry. A memory aid for the exam. Data was hard, humans were slow, models were weak, compute arrived, wins happened. That's the 8, compressed. Quiz 2. The estimation check. You flip a coin 10 times and observe 7 heads. Using pure maximum likelihood, what is p hat? And what would a Bayesian with a fair coin prior report? A. MLE 0.5, Bayesian 0.7. B. MLE 0.7, Bayesian somewhere between 0.5 and 0.7. C. MLE 0.7, Bayesian exactly 0.5, the prior always wins. D. Both exactly 0.7, priors change nothing. Think about who listens to the data, who listens to the prior, and who compromises. Pause and answer. The answer is B. MLE says 0.7. The Bayesian reports a posterior between 0.5 and 0.7. MLE is pure frequency 7 out of 10, 0.7 the value that makes the data most probable. The Bayesian multiplies that evidence by the fair coin prior, which pulls the estimate toward 0.5, landing around 0.63. Option C overcorrects. The prior never always wins, its one voice, weighed against the data. And option D dismisses priors entirely, but on 10 flips, the prior genuinely moves the answer. The follow-up worth pondering: after 1,000 flips with 700 heads, the gap between the two approaches nearly vanishes. Data in bulk wins every argument. And with that, part 1 is complete. Time to build a neural network. Part 2: Deep feed-forward networks. This is the payoff. Everything so far assembles into an actual thinking machine. Our route: we start inside your skull, with the biological neuron, build its artificial twin, the perceptron, discover why activation functions are non-negotiable, face the XOR problem, the tiny truth table that froze AI research for a decade, and watch one hidden layer melt it. Then the grand finale, the complete training loop. Forward propagation, loss, back propagation, gradient descent. By the end, the phrase training a neural network will be something you can explain, step by step, to anyone. Let's meet a neuron. Every neural network begins with an idea borrowed from biology. Your brain is a huge interconnected network of neurons, cells passing small electrical charges to each other. And here's the crucial property: the connection between two neurons can be strong or weak. That strength changes with experience. The hot pan story. You touch a hot pan. Nerves in your hand fire signals to the brain, and the pathway leading to the move your hand now neurons lights up. Because that response both that pathway gets stronger. Pathways that produce good outcomes strengthen with use. Pause on that because it's the single transferable idea of this whole section. Learning is the changing or connection strengths. In artificial networks, those strengths are called weights, and training is nothing but the systematic adjustment of weights. Practice makes perfect isn't a proverb. It's neuroscience, and now it's engineering. Let's take a neuron apart for components, and each has an artificial twin you'll meet on the next slide. 1. The dendrites, branch-like structures that receive messages from other neurons, converting chemical impulses into electrical ones and carrying them inward. 2. The cell body, the soma. It joins all the incoming signals from the dendrites into one combined signal. 3. The axon, the output cable. It transmits the outgoing message to the next neurons. And 4. The synapse, the junction between one neuron's axon and the next one's dendrites. This is where connection strength lives, where learning physically happens. The signal path: dendrites, soma, axon, synapse. Hold these 4 in mind. The mapping to their artificial versions is a classic exam question, and it's coming right up. Here's the great translation: biology to mathematics row by row. Dendrites receive signals from other neurons. In the artificial neuron, that's the inputs plain numbers arriving from other units. Synapses, the connection strengths, become the weights on each input. Strong synapse, big weight. The nucleus, producing an output from the incoming signals, becomes the computation, a weighted sum, passed through an activation function. And the axon, carrying the output away, becomes the output value which feeds the next layer of perceptrons. Vocabulary note: artificial neurons go by many names: perceptrons, units, nodes, all the same thing. And the honest caveat: this is inspiration, not simulation. Real neurons are vastly more complex. But this simple cartoon, multiplied by millions, drives cars and writes essays. So what does one artificial neuron actually compute? 2 steps. That's all. Step 1: the weighted sum. Multiply each input by its weight, add them up, and add the bias. Z equals the sum of W times X plus B. Step 2: activation. Pass Z through an activation function. A equals F of Z. That's the neuron's output. Done. Y the bias. Without B, the decision boundary is forced through the origin, like a line. Y equals mx with no intercept. The bias shifts the activation, guarantees a non-null output even for null input, and gives the model its flexibility. A homely example: a loan approval neuron. Inputs salary and credit score. Weights how much each matters. Bias the base approval threshold. Activation squash it into a yes probability. One neuron, one tiny decision maker. And the unit 1 callback, the whole layer of these neurons computes W times X plus B1 matrix multiplication. That's why GPUs rule this field. Now the question that sounds optional, but is existential: why do we need activation functions at all? Some data is linearly separable. A straight line can split the classes. Linear functions handle it. Y equals to X plus 3, output proportional to input, no activation needed. But most interesting data is not linearly separable. Curved boundaries, tangled patterns, non-linear functions, where equal steps in X produce unequal changes in Y. And here's the killer argument: watch closely. Stack 100 layers with no activation functions. Layer 3 times layer 2 times layer 1. The matrices just multiply together into one matrix. W3, W2, W1 is a single linear map. 100 layers collapse into one. The depth was an illusion. One non-linearity between layers, one sigmoid, one ReLU, and the collapse is broken. Activation functions don't decorate the network. They're what makes depth real. That's why they exist. The 4 classic activation functions meet the family. Sigmoid squashes anything into the range 0 to 1. Perfect for probabilities and binary outputs. Its weakness: it saturates. At the extremes it goes flat. Gradients vanish. Deep networks starve. Unit 1's vanishing gradient story at its source. Turn sigmoid's cousin swashing to -1 plus 1. 0 centered, nicer for hidden layers, but it saturates too. ReLU the modern workhorse, maximum or 0 and Z pass positives, 0 out negatives. Brutally cheap, no saturation on the positive side. The default for hidden layers. Watch for dead neurons stuck at 0 though. And softmax turns a vector or scores into probabilities summing to 1, the standard output layer for multi-class problems. Remember its stabilization trick from Unit 1. The defaults to memorize: hidden layers ReLU, binary output sigmoid, multi-class output softmax. That combination powers most of the deep learning world. Time to wire neurons into a network. The architecture reads left to right, which is exactly why it's called feed-forward. The input layer, one node per chore or data enters here. Pixels, words, measurements. The hidden layers, weighted sums and activations, extracting increasingly abstract features. One hidden layer, a shallow network. Several deep. Each layer builds on the last edge's shapes, objects. And the output layer, the prediction class probabilities through softmax, or a number for regression. Architecture design means choosing depth: how many layers and WIDTH neurons per layer. And notice, those are hyperparameters. Chosen, not learned, tuned on the validation set. Part 1 of this unit just became practical. Feed-forward means no loops, information flows one way only. Networks with loops exist, they're called recurrent, and that's Unit 5's story. Now for a piece of history that's also a deep lesson. XOR, the tiny function that froze artificial intelligence. XOR exclusive or outputs 1 when its two inputs differ. 0 0 gives 0, 0 1 gives 1, 1 0 gives 1, 1 1 gives 0. 4 rows? Kindergarten logic? Now plot those 4 points and try to separate the ones from the zeros with a single straight line. Try it seriously, pause and try. The ones sit on one diagonal, the zeros on the other. No single line works. It is geometrically impossible. And a single perceptron can only draw one straight line. In 1969, Minsky and Papert proved this. The perceptron cannot learn even XOR, and funding for neural networks collapsed. That's the first AI winter from our Unit 1 timeline, caused by a 4-row truth table. The Thor required one idea and it's on the next slide. Here's how the winter ended. Add one hidden layer and XOR falls. The trick: hidden neuron 1 learns OR is either input on, hidden neuron 2 learns an RBOTH on, and the output combines them, OR, but not an, either, but not both. Check all 4 rows, it works perfectly. In plain speech, you may have cake or ice cream, but not both. Probably beyond any single line classifier, cracked by 2 simple questions. But here's the deeper magic, the sentence I most want you to keep. In the hidden layer's coordinates, the OR value and the N value, the 4 points become linearly separable. One line finishes the job. The hidden layer didn't just compute. It re-represented the data until the problem became easy. That is the essence of deep learning. Every layer, in every network, is doing exactly this, changing coordinates until the answer is obvious. Quiz 3: the historical heart of this unit. Why can't a single perceptron, no hidden layer, learn the XOR function? A. XOR needs more than 2 input values. B. XOR's outputs are not linearly separable. No single straight line splits the ones from the zeros. C. The perceptron's weights cannot be negative. D. XOR requires the softmax activation which perceptrons lack. Picture the 4 points on the grid and remember what a perceptron draws. Pause and answer. The answer is B. XOR is not linearly separable. A perceptron computes a weighted sum and a threshold geometrically. It draws one straight line and classifies by side. XOR's ones sit on one diagonal, its zeros on the other. No single line can ever split them. That's the entire 1969 crisis in one sentence. The distractors: weights can be negative. Option C is simply false. XOR has exactly 2 inputs. Option A is irrelevant. And no output activation can fix a geometry problem. Option D confuses the plumbing with the architecture. And the bonus question that separates good from great: what does the hidden layer actually do to fix its site? It transforms the coordinates until one line suffices. Re-representation. If you can say that in an exam, you've understood the second half of this unit. If this lecture helped you, do like, share and subscribe to Shri Tech Bytes for more lectures like this one. See you in the next video.